Two engineers once argued so hard about which end of a number comes first that we named the fight after a children's book about tiny people cracking eggs. And that argument is still silently corrupting your data right now. This isn't ancient history. Every time a file breaks moving between machines, every time a network packet arrives scrambled, you're feeling the aftershock of a war that computing never actually settled. It's called the byte order problem. And to understand why it's so absurd, you have to understand that both sides are completely, provably correct. That's what makes it a holy war. Let's start with the actual problem. Computers store numbers as bytes. A single byte holds a small value, up to 255. But real numbers are bigger, so they span multiple bytes lined up in memory. Take the number 70,000 something, written in hexadecimal as 0x123456778. That's 4 bytes, 12, 34, 56, and 78. Simple enough. Now the question that split computing: which byte goes first in memory? One camp says, put the biggest, most significant byte first. 12, then 34, then 56, then 78. Just like you write it on paper. This is called Big-Endian. The other camp says, no, store the smallest byte first. 78, then 56, then 34, then 12. Backwards, to a human. But the computer loves it. This is Little-Endian. And here's the thing you need to sit with: Little-Endian isn't stupid. It's genius. When you add two numbers, arithmetic starts at the smallest digit and carries upward. So storing the small byte first means the processor can start work immediately. It also means a number is a number regardless of size. Read 1 byte or 4 bytes from the same spot, and the little value is right there where you'd expect it. Elegant. Efficient. Chip designers adored it. But Big-Endian has its own killer argument. It matches how humans read. Dump the memory to a screen and the number is right there, left to right, exactly as written. For debugging and for networks, that clarity is gold. So you have two camps, each armed with real, undeniable engineering advantages, refusing to budge. Sound familiar? In 1980, a computer scientist named Cohen noticed something. This fight, he realized, wasn't really technical anymore. It had become tribal. Religious. So he wrote a now legendary essay titled, On Holy Wars and a Plea for Peace. And to skewer the whole ridiculous conflict, he reached for satire. He turned to Jonathan Swift's Gulliver's Travels, published back in 1726. In Swift's story, the tiny nation of Lilliput is torn apart by a savage question: which end of a boiled egg should you crack open first? The big end, or the little end? The emperor decreed everyone must crack the little end. Rebels insisted on the big end. And Swift, mocking the pointless religious wars of his own time, had them fight, and even die, over eggs. Cohen saw the perfect metaphor. He named the camps Big-Endians and Little-Endians, after Swift's egg crackers. And those names stuck. Forever. That's why, decades later, we still use them. His point was sharp: the technical merits barely matter compared to the cost of everyone disagreeing. What matters is that we all pick one. A convention. Any convention. Just agree. But we didn't agree. And that's where the real damage begins. Intel's chips went Little-Endian. So did the entire x86 family that powers most laptops and desktops today. Meanwhile, older systems, mainframes, and crucially the Internet itself went Big-Endian. Network protocols standardized on Big-Endian so thoroughly that we literally call it network byte order. See the trap? Your Little-Endian computer wants to send data across a Big-Endian network. Every number, every port, every address, has to be flipped, byte by byte, on the way out and on the way back. Forget one flip, and disaster. The number 1 becomes over 16 million. A port number points to the wrong service. An IP address routes to nowhere. And nothing throws an error. It just silently means something completely different. This is the nightmare of endianness bugs. The code runs fine. The data looks like valid numbers. They're just wrong numbers. Corrupted in a way no crash will warn you about. It bites hardest in file formats. Save an image or a data file on one machine, open it on another with different byte order, and the whole thing turns to garbage. That's why formats like TIFF actually store a flag telling you which endianness they used. Some formats even begin with a magic marker, a byte order mark, whose only job is to announce, here's which end I crack first. An entire piece of metadata that exists purely because of Swift's egg war. And it's why in C and countless other languages there are functions with cryptic names like tom and toes. Host to network, network to host. Little rituals developers perform to survive a war they never asked to fight. Now here's the twist most people miss. Modern hardware quietly picked a winner. Little-Endian dominates. x86, most ARM chips in your phone, they're Little-Endian. Big-Endian is fading from the hardware world. But the internet's Big-Endian standard is frozen in place. Too much depends on it to ever change. So we're stuck in the strangest outcome of all. The world runs on Little-Endian machines, forced to constantly translate for a Big-Endian network. The war never ended. It just went cold, leaving every device in permanent translation mode, burning tiny cycles flipping bytes back and forth, forever. And that's the real lesson of the Holy War. The choice was trivial. The refusal to standardize was catastrophic. Cohen's plea for peace was right, it doesn't matter which end you crack, as long as we all crack the same one. We didn't listen. And so a satire about tiny people arguing over breakfast eggs became one of the most accurate descriptions of software engineering ever written.